In this video, we are going to talk about how we simplify rational expressions. So remember, rational expressions are things like this, where I have a fraction of polynomials. So polynomial on top, polynomial on the bottom. So what are the steps to doing this? I first want to factor the numerator and denominator as much as I can, and then divide any common factors in the numerator and denominator. Sometimes we call that canceling. Okay, so I want to explore when can we cancel, when can we not, through an example, and then I'll try to summarize the key facts. So first, I want to talk about a correct cancellation. So in this problem, I see that on the top, it's already factored. I got this x multiplying this x plus 1, so those are the factors that are multiplying each other. On the bottom, this 2 is multiplying the x, so those are the factors on the bottom. So there's a common factor. This x is getting multiplied on the top and on the bottom, and when I have a thing like that multiplied on the top and on the bottom, I can divide it away. So if I divide it away, that leaves me with a 1 there, and if I divide an x here, it leaves me with a 1 down there. And overall, well, I get x plus 1 on the top over just 2 on the bottom. Cool. So the technical reason why this works is with this fraction, because the factors are multiplied on the top and on the bottom, I can split it up as x over x times x plus 1 over 2. And x over x, well, something divided by itself just equals 1. And if you multiply 1 by something, well, that just equals the something. It just leaves you with x plus 1 over 2, which is what we had. So the reason why this works is, well, when the factor is being multiplied on the top and the bottom, I can pull it away and separate it like this. And when you divide it by itself, it just equals 1. And multiplying by 1 just gives you that thing. So these common factors, they kind of cancel away. So, okay. So what's an incorrect cancellation? It's really tempting when you look at this one to be like, there's an x on the top, an x on the bottom. Can I just cancel them? So I'm going to do that, and I'm going to do it wrong in 2 ways. First, if I just kind of cancel these, it seems like what I'm left with on the top is a 1, and on the bottom would be a 2. But it turns out that's not right. And now let me do it one other way wrong, which is to say, okay, if I were to divide the x, wouldn't that leave me with a 1 there? And divide that x, wouldn't that leave me with a 1? So overall on the top, I get 1 plus 1, which is 2. And on the bottom, 2 times 1 is 2. But that's also wrong. So I will cross that out. I'm pointing both of these out because they're really common errors that I see students make, and I think it's helpful to just point them out to talk about them. So why can I not do either of these? Well, I'm not allowed to divide terms that are being added or subtracted on the numerator and cancel in this way. So on the bottom, the x is multiplying the other stuff, but on the top, this x is being added to the other terms. So because of that, I am not able to divide it in the same way that I could in the previous problem when the x on the top was multiplying the other stuff and the x on the bottom was multiplying the other stuff. Okay, so here I cannot cancel for that reason. So, okay, let's flip the page. Let's do a practice problem. So for each of the following expressions, I want you to simplify it using an appropriate cancellation if possible. And if nothing cancels, then explain why. So I want to have you pause the video for 1 to 2 minutes to try these. So pause it in 3, 2, 1, pause it and try these. All right, so hopefully you paused it to try these. So with this first one, it's tempting to say, okay, I got this x plus 4 on the bottom, x plus 4 on the top. Can I divide and cancel them? Well, the x plus 4 on the top then is being subtracted by something. It's not multiplying the other stuff on the top. So because of that, I cannot cancel. So it can't cancel the x plus 4 since it's not multiplied in the numerator. Like it's not factored out of the numerator. It's being subtracted by other stuff rather than being multiplied to the other stuff. The only thing I could do with this is I got some like terms on the top. I can do 4 minus 3. And I could say that's x plus 1 over x plus 4. But that's as much as I could do. With this, I cannot cancel the x's either because both of those are being added to other stuff. Again, if I'm adding or subtracting, I cannot divide terms that are being added or subtracted. We can only do it to factors that are being multiplied in both the top and the bottom. So that said, I do see a factor in b getting multiplied on the top and the bottom. On the top, this x plus 4 is multiplying x minus 3. On the bottom, this x plus 4 is technically multiplying like a hidden 1. So because of that, I can divide by x plus 4 to leave me with a 1 there and there. So I get x minus 3 over 1. Well, that's just x minus 3. That is just x minus 3, so I can cancel. All right, so we've talked about when we can cancel on the top and the bottom, when we cannot. Now we're on to our second key point, which is domain changes and restrictions. So let's motivate this with an example. I want to simplify x squared minus 9 over x minus 3 and answer, well, what's the domain? So let's do domain first. Well, the denominator better not be 0. So my x minus 3 better not be 0. And if I add 3 to both sides, I get x better not be equal to 3. Right? Because if I plug 3 in, it would make the denominator 0. That would be bad. So now let's simplify it. So let's factor this. I notice that 9 is 3 squared. So I get a difference of squares. So I get x minus 3 times x plus 3. And then all over on the denominator, I got x minus 3. So I got x minus 3. And now this is very similar to the example we just saw in B. I do see this x minus 3 multiplying the other stuff in the top. And on the bottom, this x minus 3 is technically multiplying a hidden 1. So it is multiplying. It is a factor on the top and on the bottom. So I can divide by x minus 3. Leaves me with a 1 there and there. And then I get x plus 3 over 1, which is that's just x plus 3. Okay, so it simplifies to this. If I just look at this simplified form, it seems like I can plug any number in. Like there's nothing I could plug into this that would make me divide by 0. But in the original expression, if I plug 3 in, it's undefined because I'm dividing by 0. So what domain do I use? The one from the original or the one that I seem like I have from the final answer? It turns out we do the one from the original. So from the original, I'm going to put a comma next to my simplified answer and include this domain restriction that x cannot be equal to 3. That's important. If I cannot plug 3 into the original one, even after I simplify it, I don't want to be able to plug 3 into that either. Otherwise, technically, it's a different function. Okay, so I'm going to box this. So I haven't really been emphasizing this in previous examples, but even in previous examples, when there was something that made the denominator equal 0, it is technically something I would include next to my final simplification, this domain restriction. So I'm going to start to emphasize that here on forward. So what's going on graphically with these domain restrictions? So a value where an expression is undefined is a place where the graph is discontinuous. Like if I can't plug 3 into this, there's not going to be a point on the graph at that spot. It's not going to be continuous there. And when we cancel a common factor, like we did with the x minus 3's, by dividing it away, it kind of seems like we remove that problem. We kind of remove that discontinuity. And what that does is it creates, we'll see what it creates in the graph. We'll do that in just a minute here. But the moral is, when you are simplifying an expression, you need to preserve the domain of the original expression after simplifying it. So whatever the domain of the original is, we got to make sure we write that next to whatever that simplified expression is. Okay, so, well, what does the graph of this look like? Let's first just look at y equals x plus 3. So I'm going to draw some axes. So I'm just going to get myself ready. I'm going to draw 2 sets of axes, one for this, and then one for the original thing, x squared minus 9 over x minus 3. So I see that this is just a line. Like the y-intercept is 3. And there's technically a 1 in front of the x. So the slope is a 1. So it's an upward sloping line. Okay, so I got something like this. And then, all right, so I have that graph. So what changes if I have the exact same thing, but I have this extra domain restriction that x cannot be equal to 3? So this other one simplified to x plus 3, but it has this extra condition that, wait, we better not let x be equal to 3. I don't want to plug in wherever we are when x equals 3. I don't want to plug in like that value, wherever that one is. So, okay, let me plot this x coordinate 3 here. And I'm able to use the exact same graph anywhere except for when x equals 3. So I'm going to have the exact same shape up until when I get to x equals 3. So I'll have the same line shape with the same y-intercept. But then I got to skip over x equals 3 and then jump to the other side of it and then keep going on the line. And because I skip over it, what that does is it creates a hole in the graph. And that's what's going to fill in this blank here. We get this hole on the graph when you have a factor on the top and the bottom that cancels away like we had here. So, okay, I know for this hole, we have x coordinate 3, but what's the y coordinate? So this is where I can use my original graph. And the original graph, if I plug in x equals 3 into it, well, if I plug in 3 for the x, I would get y equals 3 gets plugged in, and then plus 3, which is 6. Okay, so that's the y value. That should be the y value of the hole. 3, comma, and then the y value 6. And that's the hole. All right, so let's end this video with an example. I'm going to up the difficulty a little bit and give this for you to practice first. So I want to have you pause the video for about 3 minutes to try this. So try simplifying this. My hint is, remember, the first step is try to factor the top and the bottom as much as we can and think about the domain. So pause it in 3, 2, 1, pause it and try it. All right, so hopefully you did that. Hopefully you paused it and tried it. So, all right, on the denominator, we got a quadratic. So I can factor this thing. So I know I'll have an x and then something, an x and something. I need two numbers that multiply to positive 12 and add to negative 8. And that's minus 2 and minus 6. Okay, that's, I think, the easier of the two things to factor. I think the top is a little tougher, but we can handle this. So I got this perfect cube here. Is 8 a perfect cube? Yeah, it's 2 cubed. Ooh, so I got a difference of cubes. So difference of cubes, remember that factors as like the first thing minus the second thing. So x minus 2. And then times the first thing squared, so x squared. And then plus the first thing, x, times the second thing, 2. And then plus the second one getting squared, so plus the 2 getting squared. Okay. Oh, and I noticed there's a common factor on the top and the bottom. There's this x minus 2 multiplying everything else on the top, and on the bottom multiplying the other stuff. It's a common factor. So I can divide it away to be left with a 1 there and a 1 there. So that gives me x squared plus 2x plus 4 over x minus 6. So I got it simplified. I just need to make sure I write my domain. And remember, we have to go back to the original to write the domain. But it's helpful to just use the factored form of the original. And I can see from the denominator that, well, x better not be equal to 6. And also from the other factor, x better not be equal to 2. So x can be either anything else except for 6 and 2. And that is my final answer. So it simplifies to this fraction, but x can't be 6 and it can't be 2.